Hello everyone. Thank you a lot for being us for today for our Jubilee 10th webinar. I hope you had a wonderful Easter holidays with your family and friends. And today we have Saša Zelenika and Petar Gljušćić giving us their presentation about their work. And dear colleagues, the podium is all yours.
Okay, thank you. So welcome everyone. It's our pleasure to be here. So in the first part, I'll try to present in general what energy harvesting is and how what are the possible applications, including those in environmental monitoring. And then Peter will give you more focused insight on what we are doing concerning really the application for bees or beehives. So let me start by just telling you a little about us. So we are from the University of Rijeka. Rijeka is a city on the Adriatic coast, a long history, but oriented towards the future. We had the pleasure also to be the European Capital of Culture a couple of years ago. So the same probably goes to the university also. We cherish quite a long history or background of higher education in the city. But today, again, oriented towards the future, we define ourselves as the European. Somebody should turn off their mics, please. Yeah. So the European University of the Future, we have 17 constituents, roughly 16,000 students, and roughly 2,000 employees. One of these constituents is the Faculty of Engineering, where we are working on. So it encompasses the studies in mechanical engineering, naval architecture, electrical engineering, computing, and mechatronics. It has 11 departments, 50 laboratories, one of which is the Precision Engineering Laboratory that is where we are carrying out our research and where the work concerning energy harvesting is then performed. One of the specificities of our university is also that we have so-called science and development centers. Currently, we have 13 of them. We are involved in 2 of them, especially in the Center for Micro and Nanosciences and Technologies. This year, we are celebrating our 15th anniversary, so dealing with everything related to micro and nanotechnologies in a very interdisciplinary way. And we have also a Center for Artificial Intelligence and Cybersecurity, where we are also involved concerning the application of artificial intelligence in mechatronics. So in general, we are dealing with precision engineering, micro and nanosystems technologies, especially the characterization of mechanical properties, optimization of the properties and of the design, and experimental validation of the structures that we are developing. All these often in the mechatronic setting, so coupling in a way the mechanical structure, electronical components, and smart algorithms to achieve the goals that we aim at. In this frame, we are dealing then also with structures devoted or related to Internet of Things, smart city, and other solutions, and that brought us towards considering sensors and sensor systems which allow to monitor some of the entities that are characteristic for various domains, among others also, again, in environmental monitoring. One of the problems in this setting is that you can miniaturize several things, but generally not the energy parts or the energy source. On one hand, on the other, that generally or in several instances, you want to monitor something in remote areas where it's not easy to deploy kilometers of cables, or else you want to get rid of batteries, which have, again, a very negative environmental impact. One way to do this is by using energy harvesting systems. So energy harvesting is defined as the process of collecting low-level energy from the environment and converting this energy into electrical energy. The physical source of this energy can be various. It can be solar energy, so light energy. It could be kinetic energy, so the energy of movements of various kinds of machines or humans or animals or plants. It could be temperature differences or other physical means. And then in collaboration with our colleagues from various institutions around Europe, we are then developing the application of these technologies in several of the areas that you see here on the slide. We are playing or working on this in this field for already 15 years, probably more, 17 now. In many instances, we involve also our students in this work. At the bachelor level less, but especially at the master's and doctoral thesis level. And again, some of these applications could be, designs that we develop could be more or less elaborate, but several of them, as in this case, can be applied for environmental monitoring, in this case, the monitoring of various values at sea. What can be shown here is that kinetic energy, especially in form of some kind of dynamic excitation, is very useful because generally, especially in man-made environments, is quite stable and ubiquitous. So you find it everywhere, and generally, or in several applications, it could be very, very stable. So how can you use it? Generally, you can use some kind of generator as a small dynamo, but often the best way to do it is using so-called piezoelectric systems. So these are special materials that have the property that when you deform them, strain them in some way, charge is created on their surface. So this is voltage, so you can transform it again, the dynamic or the kinetic energy into electrical energy. What is nice is that the energy density is quite high in these cases, and there are ways to, again, do this in very miniature settings, so with very small designs. One of the applications of this is, for example, in structural health monitoring, so monitoring of buildings, bridges, airplanes, so big structures where you can even combine the effects of the sensor itself with that of the energy harvesting device, again by using the piezoelectric properties of the material. In order to do this properly, obviously, it's not that simple always. So there are quite elaborate models to try to simulate the behavior of such devices, to try to achieve the best possible power output from these. So there are, again, quite complicated analytical models, or there are numerical models, so various, again, complexity depending on what you want to achieve. Obviously, in order to be able to really monitor all the peculiarities of the system, it has to be dynamic, it has to be nonlinear, which obviously complicates quite a lot the whole issue. And then you always have to prove what you have developed theoretically, also via quite elaborate experimental settings, often combined. So you need some kind of dynamic excitation device, but also non-contact ways to measure what is happening, so laser devices and similar. By mastering, however, these rather complex technologies, then you can try optimizing the structures, and it can be shown that by changing their dimensions, their shapes, and so on and so forth, you can achieve much higher energy densities and much higher specific powers. By doing so, then you can apply these devices in various settings. For example, we have developed a solution by which you can use the vibrations of the car while you are driving it to power a sensor of the pressure in the tires. You know that in the last 10 years or so, we all need to have tire pressure monitoring on each and every tire. So again, by using this, the motion of the car itself, we have succeeded in powering this sensor and sending the signal into the cockpit. Another interesting application is that in biomedicine. So here the problem is that our motion is generally, human motion is generally random. You cannot really assume that it's stable, and therefore you need to transform this random motion into some kind of periodic excitation of this structure. So there are interesting ways in which you can do this, again, by playing with the design of the whole setup. Use, and again, elaborated mathematical models, numerical models, optimization algorithms, often based, again, on machine learning and similar modalities. You can, again, optimize the power outputs so that you can increase the specific outputs up to 5 times or even more. And then you can, again, miniaturize everything. So, for example, that everything could be part of a smartwatch solution so that you can monitor the physiological state of patients or humans while not relying on batteries. Obviously, kinetic energy is not the only source we are playing with. We are playing also with, for example, temperature differences. Again, there are materials which allow to transform these temperature gradients into electrical energy, which can, again, be used in various settings. One of these is, again, structural health monitoring. So with our colleagues from several institutions, through another cost action, we have succeeded in showing that various modalities of energy harvesting on an airplane could be used to power the sensors that can be employed to monitor the status of the structure of the airplane itself, which is, again, technologically quite a challenging problem. And here we come to the topic of our BeSafeBeeHoney project. You can use such systems also for developing autonomous sensor nodes to monitor several of the parameters in the environment. This could be meteorological monitoring, so the general status, could be what's happening in the forest, fires, or other issues, or what's happening in the soil, so from humidity to other, in the plants as they grow, monitoring the flow of fluids in them and similar, or animal monitoring, which could be bigger animal, again, using their kinetic energy, or smaller one as the pollinators, that's the bees in our case. One interesting application on which several research groups are working currently is that of the Internet of Trees. So again, it makes no sense to deploy long cables to have a few sensors in the forest, but by powering them by the motion of air, of water, temperature differences, and so on and so forth. You can, for example, power the small cameras to see the occurrence of forest fires, or use them to power deadometers or other sensors that are related to the health or the state of the forest. Another application is that of smart farming. One of our PhD students that is currently working at the University of Tampere in Finland is playing quite a lot of these. So again, you can use the kinetic energy of the motion of animals to power small sensors related to some of the health or physiological parameters of the animal itself, or, for example, for virtual fencing, which is, again, a quite active field of research. Another project, framework project of the European Union we have been involved in was dedicated to monitoring the pollution of river courses. And there we have developed various solutions, for example, piezoelectric eels, so-called, so polymeric materials, or generators, so small generators to power again the sensors that measure several parameters related to the pollution of river courses. And this brings us also again to the subject of today, which is monitoring the state of bees in the beehive. The idea there is to use the thermal energy produced by the bees themselves to, again, through these thermoelectric generators that I was monitoring before, to transform this energy into electrical energy and power the sensors. And this is then what we are doing also in the framework of the BeSafeBeeHoney project, and what Petar will then show you within his presentation. Obviously, maybe it's better. So again, working on this specific problem, there is a quite small team. So Petar, I, and our colleague Marko Perčić. And I'm thanking you for your attention. Obviously, I think that the best way would be still to wait for the end of the Petar's presentations, and then we can have a small round of discussion, questions, and everything that eventually we want to learn more about. Thank you so much.
Thank you, Professor. I suppose we can start with Petar, and then we will have questions.
Let me try to share it. Yeah, it works, but...
Yeah, we see it now.
Yeah, you can see it without the notes, right? Okay. So, welcome. Thank you for the opportunity you gave us to talk about our little pet project here. It is a little pet project, we started fairly recently delving into these areas. It started as a combination of a hobby and professional work. So let's see if I can say something that might interest you. The key point where we start is the issue of overwintering. As most of you know, bees need to overwinter inside the hive, and while overwintering, they form a cluster. This cluster needs to heat the colony to at least 16 degrees, or if the brood is present, up to 35. The size of the cluster is from roughly 10 to 25 centimeters in diameter, or occupying 3 to 7 frames of a standard hive. What is important here is that the size of the cluster is directly related to the success of overwintering. The stronger the colony is, the larger the cluster is, the more it is likely to successfully overwinter. So it needs to be warm enough so it can defend itself, and be mobile enough to reach honey stores. You can see here a thermal image and a normal physical image in comparison of a winter cluster. Winter losses are a severe issue, especially in the temperate climates. In Europe, it goes up to around 10% to 25%. In the US, even up to 30%. Not only in the US, in North America in general. So it is an issue. Like a quarter of the hives sometimes can die during winter. The thing with colony decline and die out is that it usually occurs during winter months, and the first inspection during spring is fairly distant from the occurrence of the decline. So by the time the beekeeper finds out what's happening in the hive, the clues are usually gone due to nearby ant colonies or robbery from nearby hives. So you're never sure whether the bees starved, whether they had some disease, or you're completely clueless regarding the collapse. In this regard, monitoring of the colonies, especially during winter months, can provide a timely alarm or alert or even insight to the beekeeper in the causes of the decline. So it might be mitigated, or it might be we might learn something for the following winter. Okay. Do I unshare it? Yeah, stop sharing. Stop. You see it now? Okay. Can we continue then, I guess? So yeah, an idea of ours was to utilize the temperature distribution inside the hive to assess the strength of the colony. If you look at these thermal images, this was fairly early winters. Well, when these were taken, so the cluster is still sparsely spread around the hive, but you can see the rough form, the rough shape, and the number of occupied frames. Sorry. The idea is to use sensors to monitor the size of the cluster during winter months, and if the temperature or the number of occupied frames falls under a certain threshold, the beekeeper can receive an alert, and then go to see if something is wrong, or what exactly is wrong with the specific hive. So you can see that the higher temperature is the densely populated area. There's an intermittent area with sparsely present bees and the completely empty areas of the hive. In peak winter, this contracts even more. The temperature is, you can see in the following slide, the temperature difference between above the occupied frames and the empty frames is around 2 degrees Celsius. So it's a measurable temperature. And by simulation, it can be shown that the number of the occupied frames directly affects the, let's call it, temperature footprint above the colony. Another thing which we noticed during a bachelor's degree, a bachelor thesis done by one of our students, is that just before the honey harvest, so after the nectar flow, what does it mean? So during the nectar flow, bees collect nectar, which is full of water, and they need to expel the water from it by evaporation. And after the evaporation is done, the humidity is down, and then the honey is kept and it can be safely harvested. We noticed that there's a sudden drop in humidity within the hive just when the honey most of the honey is kept. This is not discussed with experts yet. It hasn't been discussed with experts yet, but we hope it might be used as an indication for honey extraction, but like safe honey without inspecting the whole hive, which can be a chore sometimes. The monitoring node, the sensor node itself, yeah, the presentation is a bit skewed. Sorry about that. Some bits here. The sensor node as such might be comprised of ultra low power components. So several types of sensors. We can measure, of course, temperature and humidity, but also small pressure sensors or scales to monitor honey stores during the winter. So if the honey stores fall under a certain threshold, we might intervene and bring some additional food, or something related to swarm detection in early spring, which is an issue with especially with Carnica bees. Then it will comprise also a CPU, a communication module, also ultra low power, and of course power management and energy storage. This would be a conventional type of sensor node. We estimate that at peak power above 16 milliwatts of power would be required for such a device. Where can we get this power? As it was mentioned in the previous presentation, the power can be harvested from the waste heat of the colony itself. So we showed before that there is a significantly higher temperature above the cluster during winter, which can we see here. It's about around 30 something degrees, the red line, and the outside temperature is fairly low, goes down to -10, for example, at the same time. This temperature difference can be utilized using the thermoelectric generators to generate electrical energy. Of course, the inner temperature oscillates together with the outside temperature, but with a notable offset, which also depends on the strength of the colony. But this is another discussion. If we study the temperature differences and compare them to the insolation, the lux power, like the power of the solar energy present during winter, we can see that there's a narrow area where enough solar energy is present, and it occurs at the same time where the temperature difference is minimal, but it completely disappears where the temperature difference is the highest. This might indicate the possibility to use both approaches and have a hybrid energy source. Of course, this is for winter conditions. How to utilize waste heat? So waste heat, why we call it waste heat? Because it's the metabolical heat generated by the colony, which naturally rises above the frames and gets lost through the hive roof. This is it's a normal heat flow. The energy is lost. So we can insert ourselves between these two areas and use a device called thermoelectric generator, which is a solid state semiconductor device using the Seebeck effect. And in simple terms, if we heat one side of it and cool the other side, it generates voltage. Of course, we need heat sinks on both sides, heat collector and a heat sink, and the efficiency is very low. But it doesn't have any moving parts, and it's easy to scale. Doesn't want to move the slides. I need to share it again, sorry. No, what's the problem?
You can't go to the next slide?
Yep. It's loading now. The picture is a bit large, I think. Give it a minute. It's loading here. Collapsed completely. I'm sorry, just try another thing here. Might I share a PDF perhaps? Share a PDF. Not sure what's happening. I'm sorry. Can I? Let's try this. I can't share PDF, right?
Yes, why not? Whatever it's on your screen, you can share.
Yeah, probably. Stop. Yeah. Screen. Can you see something?
Yes, I can see your PowerPoint.
Everything or just the projected one?
Everything.
We can do it like this.
Yes, please.
Sorry, I'm sorry about this. This figure is a bit big, so it doesn't want to work. So how to utilize the colony waste heat? As I mentioned before, here we need a device like this, which we then sandwich between two heat sinks. One is within the hive, one is outside the hive. So here we have the colony waste, or the inner hive temperature, and here we have the outside environmental temperature. We connected it via heat pipes to extend the outer heat sink. Used a load resistance to simulate the load, and we managed to generate a certain amount of voltage. This is just some pictures about the laboratory testing with using a controlled heat source, controlled cooling of the laboratory using standard AC, and monitoring the resulting power. For this purpose, we use the nucleus hive for less space in the lab. We also tested the device in situ on actual hives. We used two different hives. One was spread across two hive boxes. One was within a single hive box. So one was significantly stronger than the other, and combined with temperature loggers. So we monitored both the generated voltage and the occurring temperatures within and outside the hive. This is a nice and sunny day. This is a very cold, frosty day with the actual prototype. These are the two different strength hives. On top, you can see that they are very similar, but the second one, this is just the top of the huge cluster inside. These are the results. So we managed to get voltage basically throughout the night. This is just the peak temperature during the middle of the day. This is for the weaker hive. This is for the stronger hive. But this was done in different dates, different time periods. So the weather was completely different. So here we can see the temperatures went very close to each other, and therefore there was no significant temperature difference, and there was no voltage generation. But what we can see is that in a stronger hive, the offset between the inner and outer temperature is much more pronounced than in a weaker hive. We also tried to store the generated energy, where we used a voltage converter, a boost converter, a supercapacitor, and tried to charge it. We managed to charge it up to over 80% during a single week. So this is the accumulated energy, and it can be utilized for communication to the beekeeper in using a smart duty cycle. We can say once a week, perhaps, or even more times per week. So the device, the prototype is working. We can get energy, we can store the energy, but as we are design engineers, we need to consider some specific design aspects of the whole system. For example, if the system is in close contact with the colonies, we need to fall within the bee space range for all gaps in the system. What does it mean? The bee space is the gap present in the hive, which needs to be between around 4.5 millimeters up to 9 millimeters. If it's smaller than 4.5, the bees will fill the area with propolis, with resin. If it's larger, they will build comb in it, so it will all be sticky and covered. If we make it within this range, it will be clean. This is why modern hives function. So the heat sink need to be properly made or ordered or found, which falls within this gap, and all the other gaps present in the system as well. On the other hand, the system needs to be isolated from the colony if you don't want to, or you can't respect the space. You need to isolate it, so you need to block access to bees in the harvester area, which is also a completely normal thing, because this is a standard ventilation mesh typically used in beekeeping. So we use the mesh, and then we build the system about the mesh. The system should be designed to be completely compatible with standard hive components. If we want it to be used by beekeepers and to be accepted by the community, it needs to be completely compatible, not interfere with the colony and not interfere with the habits of the beekeeper as well. Insulation. In order to focus the heat flow, so most of the heat flows directly through our system, we used natural materials to insulate the area around the heat sinks. So most of the heat flows this way. We used cork to minimize the negative effects of artificial materials on the colony. However, due to the needs of the colony, we also had to trim a bit of the insulation on the edges to allow some of the moist air to escape the hive, which is very important to the health of the honeybee colony. So we trimmed it here, and then we allowed it to escape underneath the hive roof. But again, this is spread to the side, while the cluster is placed somewhere in the middle usually. So it doesn't really affect the results or the power generation. When we combine this approach with the previously mentioned sensor node, we get something like this. This is the previously described sensor node with a thermoelectric generator added to it. Again, ultra low power components, and it allows the node to be completely autonomous, and you don't have to interfere with the colony during the winter months, not exposing the brood to cold air, and not disturbing the colony. What can we monitor? We can monitor the colony temperature and the temperature distribution. We talked about that. We can monitor the hive humidity. Again, the honey harvest issue we talked about before. Then we can also monitor the food stores. We can set a threshold, and if it drops below, we can intervene with more food. And we can probably even detect swarms or swarming behavior. This needs to be studied a bit more. What does it mean? So the temperature can allow us to assess the colony strength and general health of the colony. The hive humidity can help us also determine the colony health, and probably help us with the planning of honey extraction. Food stores, we can prevent starvation and mitigate it if we manage to add more food in the right moment. And then swarm detection, prevention of swarming, and management of swarming, which is again a chore during early spring. This is about it. Thank you very much for your time. Thank you very much for allowing us to talk about this project of ours. And please feel free to ask questions if you are interested in any of these topics.
Thank you a lot, professors, for giving us such wonderful presentation. We have a few questions here from Alexandra Lavgonska. Okay, first question. You need only 16 milliwatts to empower the whole systems. Is it possible, I suppose?
It's peak power. It's the power required at the moment of maximum power consumption. So it's a lot of power. 16 milliwatts is a lot of power. But if we manage to accumulate the power and then use it only at fraction of time when we need it, just a quick burst of power when we need to send the data, it's usable, it's doable. So we don't need to power the whole system all the time.
Okay.
This is why I mentioned duty cycles. So we can take the measurement once per day or twice per day, and send the data once per week, or send the data only if it exceeds a certain threshold, as an alarm, for example. But it's still a work in progress.
Okay, and just to catch up on this question, is it possible then the solar energy and this type of energy harvesting, is it possible to power the whole system in the beehive?
I think it should be, yeah. But again, we are still working on it.
Okay, yeah, it's experimental setup.
Yeah. No, it's the prototype generator works, and we can store the energy, but we still have to build the node. We need to build the node. It's currently being considered and worked on, but still we don't have the results. I have a written question here, so if you don't mind, I would like to answer that. I don't know if you need only 16 watts per, yes, this is, we need 16 watts, as I said right now. How many temperature sensors are there in the hive during winter? 30. Now we didn't have 30, but yeah, I did mention 30 or even more because we want to get a two-dimensional map of the temperature. But the temperature sensors are very low power components. And again, if we manage to get the reading once or twice per day, we only need to power them once and twice per day. So it's all about the duty cycle. Information is transmitted only twice per day at a specific point in time. Yeah, I think I did answer the transmission thing. It still needs to be defined, but it's about the duty cycle again. If we manage to send more often, it will be amazing. If we manage to send it once per week, it will be also good enough. So, because it's a very slow process. You're welcome.
I have one question only. How much does it cost to build such an experimental hive? Because I'm working on something similar here in Belgrade, and this is really nice idea to have a power generating system instead of sunlight. Suppose when there is snow,
but there is no sunlight.
yeah, and this is really a nice idea to power the system.
It's not that much. I mean, you can contact me via email, so I can send you the links if you need. But it's not that high. The most expensive component is the DC-DC converter, which is a specific type optimized for very low startup voltage. It has a very low startup voltage. It's optimized for thermoelectric generators. That bit is the most expensive component.
Okay.
And I would be very happy to cooperate with Poland as well. Thank you. Anyone else? Okay.
If there is no one else, I would like to thank you again, professors, for giving such nice presentation, and see you in 1 month for next webinar. If there are any candidates, please contact me, and we will see what we can do to organize such a nice event.
And obviously, you, Nemanja, or the colleagues that are interested in collaboration, yes, please give us, send us an email and we can set up,
of course,
something together. Yeah. Thank you a lot.
And sorry once again for the technical problems.
No issues. Thank you all. Bye.
Thank you. Bye.